Okay, so let me talk about the some of the implementation details in here, more specifically about the big picture of the data structures used in this assignment. I think this is the most challenging part of the assignment, being able to visualize what the data structures look like and how they're organized. Right, so now we know that we're gonna want at least a hash table and an array of something. But let's start from here. So at the beginning we're gonna have a small data structure. It's just a struct in C, and the type is gonna be SIMTable C. SIMTable T, and it's gonna contain 3 members. So the first member is gonna be a hash table, which you'll notice is a double pointer. Hash table. We'll see why it's a double pointer. Then we have another member called address table, and I believe that's also yes, that's another double pointer. And then we have size. Right, so this SIMTable is not really going to contain our symbol table. It just contains pointers to part of our programs that contain the actual data. So the hash table is going to point to the array that is going to be our hash table. So it's going to be an array of a specific size, and the size is passed to you as a variable. You can specify it when you start the program. So let's suppose, for the sake of argument, that our size is 4. And initially, so all of these are pointers actually. Remember from the previous video that this is going to be a hash table of heads to linked lists, and the head is just a pointer to the first node. So all of these are pointers. So this is an array of pointers, and the pointer type is node T pointers. So node T pointers, so node T is the data structure that we're going to use to encapsulate a node in a linked list, in the linked list. Initially, because the hash table is empty, all of these should be initialized to null, so that they don't point to any linked list. Alright, now the size, you're going to store it in this particular member, in the size member. That way you can keep track of the size of the hash table. Now let me talk about address table later. First, let us talk about how we're going to represent a linked list. So let's suppose that we have so these are the indexes. Let's suppose that we have an element and we're going to insert it at index 1 over here. So the first thing that happens is you're gonna create a node, and all this is done dynamically, a node T, and you can visualize it like this. And the node T's structure has 3 members. So the first one is the hash. So remember that when you add something to the linked list, you have to calculate the hash, and we just want you to store that hash in here. Okay. Now the next member is next. So this is a node T pointer because it points to the next node in the linked list. So you might imagine that there's another link to another node that has its own hash and its own next, and the last node in the linked list has a next of null, so to indicate that that's where the linked list ends. And then we have something here. We have a structure inside this structure, and the type of this structure is symbol T, and it encapsulates the name and address pair for the symbol. right? So that's where you'll find like ABC and 6, because that's ABC is the name and 6 is the address, something like that. So the address is very simple. The address will be an integer, so address will be an integer, and then the name will be a string, but the string will be stored inside there. Instead we're gonna have a pointer to a string that is dynamically allocated. So please refer to the documentation for details on that particular field. There are some important notes in there. So you'll have a pointer to the beginning of this string, and that will be A, B, C in our case. Right, and the same will happen to the other node, address, and then it will have its own pointer to its own name. So let's suppose that this was XYZ, and so this linked list should actually be linked to here. Oops. All right, so that's how we represent the nodes in the linked list. That's how we encapsulate them. So this is a node T, and I'm not gonna write it to because it's too cluttered. The inner structure is a symbol T. Okay. Now there's something else that happens when we insert something to the hash table. And it's the problem of that if we have the name that we're searching for in a hash table, we can calculate the hash value and we can calculate the index, and then we go to that linked list and try to find the element in there. But let's say that we're not given the name, but we're given the address. So an address lookup in this hash table is not efficient because the hash was not based on the address. We would have to go through all linked lists, all entries, and until we find a symbol that has a specified address. So instead of doing that, we're gonna keep track of another array, and that's where the address table comes in. So the address table is not gonna be exactly a hash table, although you can consider it to some extent like that. But what it's gonna be is gonna be an array. And it's gonna be an array of chart pointers. So array of chart pointers. And it's gonna have a constant size always, and that size is gonna be 2 to the 16. And it turns out that it's 2 to the 16 because we have 16 bits in the LC3, and with 16 bits we can represent 2 to the 16 addresses. And so what will happen is that every time we insert a node in the linked list, let's suppose that this one has an address of 2. We're gonna go to the index corresponding to that address, so that will be 0, 1, 2, and we're gonna make that index point to the name of that symbol. So it will look something like that. Now the advantage of this, and I need to make sure that I indicate that this is linked to the main SymTable T structure. The advantage of this is that if we want to look something up by address, we're not going to go through the hash table. We're going to go to the address table. We're going to go directly to the address that we're looking for, and that will point us directly to the name. So that's very fast. So now we have two ways of looking up information in a quick manner. Now there are some corner cases that you have to take care of, and they're described in the documentation. And one of them is, what if you get another symbol whose address is 2? That's perfectly legal. what you'll do is you'll insert it normally in the hash table, but you'll check if there is something at 2 already. You will leave it alone. You won't change it. You would leave it pointing to where it was before. That way, the address table is pointing to the first symbol with a given address. What is not legal is to have multiple symbols with the same name. So when you are going to insert stuff into the hash table, first you have to search to see if that name is already there. But that's not going to come until part B. In part A, you'll be dealing with the function @unique, in which you can assume that there's not going to be duplicates. I'm not going to test that function with duplicates. So you can assume that you can insert it. You don't have to do a search. And sorry, that's part A. Now you'll have a few functions in here, so let me describe them quickly. The symbol init function is going to allocate enough space for this part of the data structures. So it's simply going to initialize symtable t, and it's going to initialize the array of no t pointers, the hash tables, and the array of characters. And I should say that initially, all these elements in the address table are also null because they're not pointing to anywhere. So you have to allocate dynamic memory for these three things, these three structures, and you have to initialize the hash table and address table to contain all nulls. So think about the difference between using malloc and calloc for the purposes of this. And remember that null is the same as 0 for systems. In the other function that you have to implement is the add function. So that's when you have to go to the you have a node and you have to allocate that node directly. You only have the symbol name and the address, and you have to wrap that into a node. You go to the right index that you calculate using the hash value, and then you have to insert the node. Let's say that it goes here. You have to insert it at the beginning of the hash table. That's very important, because if you don't do that, if you don't follow that order, your output will be wrong. Now the next function that you could that you could write is find by address. And since you completed add unique, then find by address is just gonna be passed an address, and you have to return a pointer to the name. So that's a simple lookup on this table. Now, and the last function is going to be iterate, for part A. And iterate, what it's going to do is it's going to go through all the nodes in the hash table, and it's going to call a specific function for the symbol inside each node. So basically, you'll have a loop that's going to iterate through all the entries in the hash table starting at index 0. And then if there's a linked list in an entry, then you go through that linked list in order from the head to the tail, and you call the function for each node. And then you move on to the next index until you've covered all the linked lists in the table. For each one, you'll be calling a function, and the function that you're going to call is called through a function pointer. So how to do that is described in the documentation. It's a very interesting concept. And that way you can complete part A, and you can test it as you go. So first you have to write something for the add function, and then once you write the find by address, you can test to see if that part of the add function works. And then you can test with iterate to see if it really inserted everything, because iterate is called by two commands. One is list and the other one is count. So if they give you the right information, and you have to make sure it prints in the right order, so you might want to do all this by hand at first to determine the order. If it gives you the information in the right order, then you're good. All right. I'll make another video later to talk about part B if necessary. Good luck.